Hello everyone, welcome to another episode of Chemistry Simplified with Rosaline. Get ready to become a titration expert as we unlock the mystery behind titrations today. Grab your pens, your notebook, and let's go. So what exactly is titration? Let's look at the definition. Titration is a process whereby a solution of unknown concentration from a graduated burette is being added to a second solution of known concentration in a conical flask until a chemical reaction between the two is just completed, meaning there's a solution of unknown concentration in a burette that is being added gradually to another solution, the second solution, found in the conical flask until the chemical reaction between the two solutions is just completed. That is the definition of titration. Titration is sometimes referred to as volumetric analysis. Titration, volumetric analysis are one and the same thing. Let's take a look at some terms used in titration. To understand titration, we need to know a few important terms as we will be using them along the line as we proceed. So the very first one we'll be looking at is the titrand with D, or the analyte. The titrand or the analyte is the solution of unknown concentration, and during titration it is always found in the burette. The second one is the titrant with T, or the standard solution. We already know what a standard solution is. A standard solution is a solution of non-concentration. That was our topic last class, and during titration it is always found in the conical flask. The third one, let's look at the equivalence point. The equivalence point. The equivalence point is a point where the number of moles of the titrant added is exactly equal to the number of moles of the titrant present. The next term we have on the board is the endpoint. What is the endpoint of a titration? It is a point where a detectable color change indicates that the reaction is just completed or the reaction has ended. Endpoint is always a drop away from the equivalence point. Let me explain. As you add the analyte from the burette to the titrant in the conical flask, there will come a point when the analyte added is exactly equal to the titrant present. That is the equivalence point. But at the end point, you are going to add more of the analyte. When you add more of the analyte and all the titrant has reacted, meaning there's no titrant again in the conical flask, the extra analyte added, just a drop, is going to react with the indicator. Note that when you put the titrant in the conical flask, you add an indicator to it. So a point where the analyte added is going to react with the indicator instead, because all the titrants present is finished, is called the end point. At that point, when the analyte reacts with the indicator to give you a color change, it is called the end point of a titration. Hope it is clear. And then the indicator is a substance that will change color in the presence of an acid or a base, or that will tell you if the reaction is completed or the reaction has ended. We continue with the types of titrations. There are four main types of titration we'll be looking at today. The very first one is the acid-base titration, sometimes denoted as ABT. Acid-base titration is a neutralization reaction between an acid and a base, where an acid reacts with a base to give us salt and water. The second is redox titration. It is a titration where oxidation and reduction takes place simultaneously. That is, one species undergoing oxidation and the other undergoing reduction at the same time. We have complexometric titration. In this type of titration, an analyte reacts with a titrant to give us a complex. And of course, the fourth one, we have precipitation titration, where an analyte reacts with a titrant to form an insoluble solid. Those are the 4 types of titrations we have. Let's continue with the choice of indicators when working on titrations. What are the titrations we use when we are working with acids and bases? The first one, when we are titrating a strong acid against a strong base, what is the indicator we use? We use any indicator. Any indicator can go for a titration between a strong acid and a strong base. Example of a strong acid, hydrochloric acid. Example of a strong base, sodium hydroxide. The second one is a strong acid and a weak base. Which type of indicator can we use? The best or suitable indicator for this type of titration is methyl orange. Strong acid like nitric acid, sulfuric acid, and a weak base like sodium carbonate. The third one is the titration of a weak acid and a strong base. A weak acid and a strong base. The type of indicator that we can use is phenolphthalein indicator. And then the fourth one is a weak acid and a weak base. For this one, no suitable indicator is available. There's no suitable indicator for a titration of a weak acid and a weak base. An example of a weak acid is methanoic acid. Let's look at the colors of the indicators in acidic and basic solutions, or acidic and alkaline solutions. We have a table on the board, a table that gives indicators and their colors in acidic and alkaline solution. An alkaline solution is a soluble base. An alkaline is a soluble base. We have blue litmus, methyl orange, methyl red, phenolphthalein, and red litmus. And we can see the colors in acidic solutions and in alkaline solutions. Now things are getting hot in here, and we are going to enter the lab and titrate a solution. We have a case study on the board. It says, use the prepared standard solution in a previous class to determine the concentration of hydrochloric acid. Your description should include the collection of data and interpretation of results. In our last class, we prepared a 0.1 molar standard solution of sodium carbonate. We are going to use this standard solution we prepared to determine the concentration to titrate hydrochloric acid. Okay, why did we say we are entering the lab again? That is the aim of our experiment. To determine the concentration of hydrochloric acid using 0.1 molar sodium carbonate solution. That is a standard solution we prepared last class. Let's start gathering our equipment. What do we use? We need that standard solution of sodium carbonate. We need our hydrochloric acid. We need distilled water. We need the burette, distilled water to wash our equipment. We need a burette. We need a pipette. We need 3 conical flasks. We need a beaker. We need clamp and stand. We need methyl orange indicator, and we need a white paper or a white tile. So let's take a look at some of the images of the equipment we'll be needing. As I draw, follow up. There are some that you already know from our last class during the preparation of standard solution. We have a clamp and a stand, conical flask, funnel, burette, pipette, as you can see, and our prepared standard solution in the volumetric flask. Now let's look at the procedure you follow when you want to standardize or titrate your solution. The first one is that you have to wash all your equipment very well using distilled water. Wash all your equipment very well using distilled water. After washing all the equipment, you are still going to rinse the pipette with the standard solution, because the pipette is going to contain the standard solution. You rinse the pipette with the standard solution, and you rinse the burette with hydrochloric acid, because the burette is going to contain the hydrochloric acid. The first image we have seen with the orange solution is the burette, and the one containing the yellow solution is the pipette. Those are the images. After washing and rinsing all your equipment, what next? The burette is clamped and filled with hydrochloric acid up to the 0.00 cm cube mark. Remember, the burette is filled with the hydrochloric acid, solution of unknown concentration. Next, you record that 0.00 cm cube mark as your initial burette reading V1. And then next, you take your pipette. The volume of the pipette is 25 cm cube. There's a mark on it. You pipette exactly 25 cm cube of 0.1 molar standard solution into a conical flask. 25 cm cube of your prepared standard solution. You suck it out using a pipette, and then you transfer it into a conical flask. Now your burette is clamped and filled to the 00 mark with hydrochloric acid. Your conical flask contains the pipetted 25 cm cube standard solution. The next thing you have to do is to add 2 to 3 drops of methyl orange indicator. Why the choice of methyl orange? Why are we using methyl orange indicator? We know that sodium carbonate is a weak base and hydrochloric acid is a strong acid. And titration of a weak base and a strong acid, we make use the indicator that is suitable for such a titration is methyl orange. We should also note their colors. We have seen it previously. The color of methyl orange in a basic solution, sodium carbonate is basic, is yellow, and at the end point is going to change to pink. After adding the 2 to 3 drops of methyl orange indicator, we are going to place the flask under the clamped burette on a white background or a white tile. You can look for a white sheet of paper and put it under. The reason we are using a white sheet of paper is to make sure that when there's a color change, we'll easily see it. And then we are going to be running our acid from the burette slowly into the conical flask while swirling continuously. Next, we continue adding the acid slowly from the burette into a conical flask until there is a permanent color change. This color change, the color we are expecting at the end of the titration, should be a pink color. When there is a permanent pink coloration, that is the end point of our titration. We note the final burette reading and we record it as V2. Hope we are still in class. So let's write on. After that, what are we going to do? We are done with our titration. We have had our initial burette reading and our final burette reading. We are going to carry out 3 different titrations. You follow this procedure 3 times. Now you get another conical flask. You pipette 25 cm cube of the standard solution into the flask, and then you refill your burette, and then you start titrating. So you are going to have 3 conical flasks. The first one you are going to titrate, we call it the approximate. You don't use the approximate in calculation. That's just like a rough work. And then you become more accurate when you are working with the first accurate and the second accurate. The first and the second accurate are the ones that are used in calculations. You use just the first and the second accurate titrations to carry out your calculations. So you have to be more careful when it comes to accurate 1 and accurate 2. The first is the approximate, the second is the first accurate, and the third is the second accurate. I repeat, you use only the first accurate and the second accurate to carry out your calculations. Let's have some visuals. This is our standard solution that we prepared in our previous class. And then we have how many conical flasks? We are supposed to have 3 conical flasks. When you use a pipette, we have seen a pipette on top of one of the conical flasks. When you use a pipette, you suck out your standard solution, 0.1 molar sodium carbonate solution from this flask, this one that is having the eye, and then you put it into your conical flask, the flask numbered 1. After that, what do? You add your indicator. This second one written a pipette is not a pipette, it's a mistake. It's supposed to be a dropper. You use your dropper to drop 2 to 3 drops of methyl orange indicator. What do? Your burette is filled to the 00 mark, the one in orange or yellow color, something like this. It is filled to the 00 mark. You note the volume. You put your conical flask under the burette, and you are running the acid, slowly and swirling the conical flask. On the fourth flask, you are seeing that the volume of the acid in the burette keeps on reducing. And then on the fifth flask, we have had the color change. That is the end point of your titration. You note your final burette reading. And we are saying that you are going to carry out this procedure 3 times. The first is the approximate, the second is the first accurate, and the third is the second accurate. And we use the first accurate and the second accurate in carrying out our titrations. Hope it is clear. Our case study demanded the collection of data. Now let's collect our data. All right, we have final burette reading, we have initial burette reading in cm cube, and then we have volume used and best results, where we have 1 indicates the first titration, 2 indicates the second titration, and 3 indicate the third titration. We say the first titration is called the approximate, which we don't use in calculation. That's why in best result it is not ticked. The second one is the first accurate, and we use it in titration, so it is ticked. The third is the second accurate, and we use it in titration, and it is ticked. Look at the initial burette reading. Go to initial burette reading. Are you seeing that? Under 1 we have 00. That was after filling your burette to the 00 mark. You take the reading as 00. It is same with the second, meaning after titrating, you refill again to the 00 mark before you start. Same with the third. Let's go to 1. After the 00 mark, after running out the acid from the burette, we ended at 22.65. That gave us the final burette reading for the first titration. And then for the second titration, we ended at 22.40 cm cube. And then the third titration, we ended at 22.50 cm cube. We assume that those are assumed values. It might be the same for me and then different for another person depending on the masses we are using. Let's assume that this is one of the data we collected in the laboratory. Now we have our values, the data we have collected. How do we calculate? Bearing in mind that in calculation, we ignore 1, which is the approximate, and we work just with 2 and 3. Let's move to our calculation. How do we get the titer? The titer is the volume of the acid used. The volume of the acid used. We said we use only 2 and 3 when we are doing our calculation, so we are assuming that 1 never exists. In our formula, volume 1 plus volume 2, we are working just with 2 and 3 here. If you take, let's go to titration number 2. If you take 22.40 minus 0, you still have 22.40. That is the first volume we are using, 22.40. Let's go to titration number 3. If you take 22.50, take away 00, the volume used will still be 22.50. So our volume used to will be 22.50. And then we combine and take the average. The formula says to have the titer, which is the volume of the acid used, you take V1 and V2, volume 1 and volume 2. That is the first and second accurate, and then you divide by 2. Our first accurate gave a volume of 22.40, second accurate gave a volume of 22.50, and then we divide by 2. When we divide by 2, what we are going to be having, or what we will have, is 22.45 cm cube. That is our titer. That is the volume of the acid used to neutralize the sodium carbonate. Titer and volume of the acid used to neutralize the sodium carbonate are one and the same thing. If you are asked to calculate the titer, this is what you will do. If you are asked to calculate the volume of the acid used, it is still one and the same thing. Don't get mixed up. The reason why we are carrying out this titration is to determine the concentration or the molarity of hydrochloric acid at the end of the day, using the solution of what we know, using the concentration of what we know to determine the concentration of what we do not know. We know the concentration of our standard solution sodium carbonate, which is 0.1, but we do not know the concentration of hydrochloric acid. How then can we determine the concentration of hydrochloric acid? Knowing the concentration of sodium carbonate, the volume of the hydrochloric acid used, and the volume of the sodium carbonate used. Here is the formula. It states molarity of acid Ma times volume of acid Va divided by molarity of base Mb times volume of base Vb equals number of moles of acid Na small n divided by number of moles of base small nb, or concentration of acid Ca volume of acid divided by concentration of base volume of base equals number of moles of acid and number of moles of base. From this formula, we have seen that molarity and concentration are one and the same thing. So when you see any of this formula, know that it is the same. Molarity, concentration are one and the same thing. So note that. So we are going to be writing our balanced chemical equation between sodium carbonate and hydrochloric acid in order to obtain the number of moles of the acid and the number of moles of base that reacted. Let's look at the equation. Sodium carbonate plus hydrochloric acid to give us sodium chloride plus water plus carbon dioxide. When an acid reacts with the carbonate, it gives us salt, water, and carbon dioxide. Of course, we need to balance the equation. So we have to put 2 in front of the hydrochloric acid and 2 in front of the sodium chloride to balance chemical equation. If you don't know how to do that, you watch our previous videos and you learn that from there. We see that from the balanced equation, number of moles of acid. In front of hydrochloric acid, what do we see there? The figure we see there is 2. So number of moles of hydrochloric acid reacting is 2. From the balanced equation, let's go to number of moles of base. The base we are working with is sodium carbonate. There's nothing in front, meaning there's a 1, even though it's not written there. Note that there is 1 in front of sodium carbonate. Whether it is written or not, know that there is a 1 there. So the number of moles of sodium carbonate reacting is 1. And the number of moles of hydrochloric acid reacting is 2. So we have had our Na and our Nb. So let's make molarity of acid or concentration of acid the subject of the formula in our equation. You should know how to make subjects of formula in equation. And if we do that, we will have molarity of acid as molarity of base times volume of base times number of moles of acid divided by volume of acid times number of moles of base. Let's substitute our values into the equation Ma. So Ma is equals to 0.1 molar. 0.1 molar is molarity of base. Molarity of base. Our base is the sodium carbonate. The concentration or the molarity was 0.1 molar times volume of base. The volume of base is the volume of the pipette. We pipetted 25 cm cube of the base from the volumetric flask to the conical flask. That is the volume of the base, the volume pipetted. That's the volume of the pipette, which is 25 cm cube, times number of moles of acid. From the balanced equation, we said Na, which is number of moles of acid, was 2 moles, divided by volume of acid. The volume of acid is the titer, the volume we ran from the burette, the titer, the one we calculated previously, and we had 22.45 cm cube. Please don't forget, the volume of the acid is the volume we refer to as the titer, the one we summed accurate 1 and accurate 2 and we divided by 2. And we have our titer. We said that was the volume of the acid. We are saying that it gave us 22.45 cm cube times number of moles of base. From our balanced equation, we had 1 mole. If you do the maths of this, you are going to have 0.2 molar as the concentration or the molarity of hydrochloric acid. Congratulations to you. You have determined the concentration of hydrochloric acid by titration using the concentration of sodium carbonate. Thanks for joining and see you in our next video.